Hello everyone and welcome to Handmade Heroes, show where I code a complete game live on stream. We ended in a very fortuitous place yesterday, actually. We kind of, I don't know, we just had a good day, I guess you would say. The both things I wanted to look at and try to do just kind of worked. It seemed like right off the bat, and maybe we've got some lurking bugs in there because we haven't really gone through it with a fine-tooth comb, but it was pretty great. And so if you take a look at where we ended up, we put in some testing that we were going to, we turned all the reflectors red so we could tell the difference between direct light and indirect light, for example. But if you take a look at where we left off, we have some nice ways of looking at now what's going on with the lighting, and it really has improved rather dramatically in a number of ways. There are still some things that we want to start looking at now, but it's quite nice with the way that it's actually permeating the world, right? And you can kind of see when we take a look at how much more solid the localized lighting is. It doesn't leak through walls, it doesn't really leak through the floor. Like, you still get some lighting here just from interpolation, but you can see that the actual light probes don't pick up lighting through solid objects anymore like they used to, just because of the way that the blending was working. So we've really got a pretty solid version of the lighting now, and mostly our problem at the moment is just how do we now start to improve the quality level of the light solution so that we actually kind of more know what these values actually are, and we can have sort of an idea that we're actually producing stable results. Because even with our upgrades from yesterday, we haven't addressed like feedback problems. So do you see, you can see here there's like these weird feedback problems that occur as I'm moving. There's lag, right, in the lighting. As you know, there's some lag in the light, and as I spread the light out, it kind of has like a feedback effect, right, where lighting that's left in the world is obviously not always converging towards a stable state. It can sometimes feed back on itself and produce more lighting. And the red that you see here, like I said, is the secondary lighting. It's lighting that's being picked up from reflectors. And you can see how there's just a big difference depending on how I do things. Here's the lighting when I stop in this room, but you saw how red that it got before when I was just moving through it. And so that's really, I think, the last big thing that we want to tackle. There are a bunch of cleanup things that we want to do once we're pretty happy with how the lighting solution's actually working. But in terms of getting to that point where we're really happy with it, that feedback is just a little bit of a problem, right? And so what we'd like to do is figure out some way, because you saw, I mean, hopefully if you've seen the past couple episodes, hopefully you saw just how important and powerful it was to draw everything that we wanted to look at. Because when we are, when we're trying to debug things, we're looking for insight, and when we're trying to improve things, we're looking for insight into how the system's working and how it might work better. And every time we introduce some kind of a visualization like this, where we can see what the lighting is actually producing, it's really pretty dramatic in terms of how much insight that can give us. And so the problem that I think we have right now is this visualization allowed us to really effectively attack the problems of the light leaking through various places and other problems of that nature. So what I think we need to figure out now is, how do we create a system that shows us something about the energy propagation, so we can actually start to think about how that has to work. And one of the things that I think we need to do is we need to, now that we know that this is pretty much our final scheme, we need to produce some idea of what the actual physical quantities are of the light. So I would say going forwards, primarily what we need to do is figure out some way of visualizing the energy levels and how they are, what they mean and how they're balanced. And then the other thing that we want to do is then start to look at the render side. So probably, looking at this interpolation, it's a little bit too square, and I think we probably will can do things that will make it more diffuse, that'll spread it out more, and that'll hide some of the artifacting that you get because we're sampling on a regular grid, for example, right? And so what we want to be able to do here is we want to be able to progress towards that lighting quality goal using some visualizations that will let us see what's going on there. And these are pretty good visualizations for showing things like the fluctuation of power in the lighting. And so it's not that we don't have like something, right? Like this shows us something that we can look at, and we probably need to clamp it down a little bit because if you take a look at how strong these directions are, they grow a little bit too much, right? So probably we would want to in here, if I just load up the Handmade Hero lighting system here, there we go. When we render our octahedral maps, we probably want something that will scale these values in maybe like a clamped fashion, probably. So you can see here we've got a scale, and I don't know, there's different ways we can draw it, but we could actually even not use the intensity for that. We could just draw the color, right? So another way of looking at this would be we could just do that, right? We could say, we're just always going to draw a little ball, and we don't actually make them longer. We just make them change color. And so then what you can do is you can look at these little, at these little balls here. And I like that because it never gets out of hand, but I do think maybe we want just a little bit of a hint there. So I think what we might want to do is just have a clamped 0, 1 of the intensity. So, imagine something more like, let's say we do this. So this way we are taking a little bit of that intensity into account. So as those lighting values get larger, we will, produce increased length so we can see a little bit just to provide like a spatial visualization component to it. But this way they'll never grow like without bound, right? And I think that's, more what we want. What I will say is it's a little weird that they flash to me, right? I can't say that I understand why that's happening, and it's a little bit disquieting. Because when you look at how that pattern is occurring, oh, you know what? That's just the alpha, is what that is. If I do this, that won't. Yeah, okay. So as we move around the world, as you can see here, we can now kind of more cleanly see the directional components of these things. They don't grow without bound, and that's good. Again, this doesn't really help us with the power thing, but it just keeps this visualization working a little more smoothly. And if you want to look at any particular part of it, you can still go in there. And it does sort of have a fairly clean directional component to it. And you can also still see the low colors because they never get too small, right? But you can see where that light is coming from. And so now if we start to move on to the next part of what we sort of need to do, there's a couple things we could start to talk about. So one of them is if you take a look at how this this room is set up here. So it's actually kind of hard to control that way. I think it could be right about there. I don't know if that's the rough center of the room. Yeah. So if you take a look at that, I'm just curious to what extent we're getting accurate bounce lighting. And if I look at it, it's like, it seems somewhat plausible, right? Like I'm not seeing a lot of weirdness there. It seems fairly reasonable. And so I just don't think there's much left to debug in just that one aspect of it. So I think we do want to now move on to just like, let's take a look at the power distributions here and how those are working. There's some things we could do to reduce the flicker, and I think we probably want to do them, but it's kind of it's a little bit weird. I thought of a pretty obvious way that you could substantially reduce the flicker, and I just don't know if it's good or not. So that's another thing that we could choose to do. I don't know if we really want to do that yet, though. It seems like the flicker is fine for now, because the flicker is not really it's not interfering with my ability to see what's going on. It's just like a constant level of noise that's superimposed on top of the data. And because there's really no harm in that, I think I'll leave the denoising, which I actually think I have a pretty good idea of how I want to do. And I'll leave that for later. So right now, let's talk about how we manage the power level in these things. So I think what we want to do is I want to talk about lights as having a particular amount of flow coming out of them. And this is the way that I liked to think about it before, in terms of how I can go about creating a stable system, or hope to create a stable system. I'd like to think about lights as having a particular amount of power that they're putting out into the world. And what I want to do is I want to make it so that amount of power can bounce around the world without generating more. So when you look at a particular place in the world, it should be the case that you can never have any surface with more light than the total power of the lights that are directly hitting it, right? And just to give some perspective on what that means, and where I think we're kind of going wrong, I'll do a little diagram here. Fundamentally, what we'd like to do with this system is say, well, we know there are some lights in the world, and we're going to say that each of these lights has a particular power associated with it, or maybe for our purposes at the moment, I'm just going to call that the amount of flow, like how much flow is coming out of these. So we might have an F0 and an F1. That's the amount of flow that's coming out of the lights. And this is in R, G, and B, so they can be colored lights, but I don't actually care about that right now, because as far as I'm concerned, each R, G, and B are basically separate light channels, so it's sufficient to talk about any one of them. We could just talk about the red channel, and that's sufficient. So if you think about what's going to happen, a surface in the world that's reflecting light, if two light sources are both incident on this surface directly, so this surface can hit both light sources, I want to have no more than F0 plus F1 reflected off. Okay? So this should be the maximum possible. If this surface is somehow set to 1.0 reflectivity, a mirror basically, a perfect mirror, it should never be able to achieve a value fundamentally higher than that. Excuse me. And so what we need to do is figure out how to ensure that through all of our light sampling, this cannot be violated. And right now, we basically know that it can be. So what we're seeing right now is something like this. We have a light reflector, and then maybe we have, I don't know, say another reflector over here. And what we're seeing is that somehow, we reflect light in this way. So we have two light sources. They're both incident on this and incident on this. And somehow this then gathers from here even more light. So maybe this guy is reflecting F0 plus F1 at first, and this one is reflecting F0 plus 1 at first, but then it's like additive. So it's taking this light and it's becoming now even this other thing where we're actually adding another term in here. And we're getting brighter than our light sources. And so what we need to do is go through how our light is being propagated and stop doing that. What we need to do is look at the lighting that's incident on a surface and produce answers for, say, our lighting probes that make it impossible for you to generate more light than you were previously having. Since the way we currently do things is all we're doing is taking samples of what light is out in the world and averaging them, I think I have a pretty good idea about where we're going wrong. And where we're going wrong, I think, is in our diffuse blur. So I think what's happening is that currently, here in the diffuse weight maps, the problem that we have is we're taking a like a spectral light source, and you can see here that we're summing basically like over a hemisphere how much light is incoming, and we're pre-creating an energy value here, right? And the problem that we have is this is completely wrong. This is basically saying, look, if I have two, and you know what, I don't know why I put the blackboard away. I guess I just wanted to go to this real quick, but we should talk about this on the actual blackboard. So if you think about what this is doing, we have an octahedral map, which, is basically a way of encoding the lighting on the sphere. And so we're saying that for a particular location, right, we've got this sphere, and we happen to be encoding it in an octahedral map, but that's really incidental. Doesn't matter how we're encoding it. The point is we have a collection of light samples on the sphere. And what we're doing is we're saying, well, we produced specific samples in our specular encoding. So we have a specular map. And the specular map is what we actually encode. So if we have a direction here and a direction here, we know the lighting at these two directions. But then what's happening is we're producing a diffuse map. And the diffuse map is saying what, we don't really need a diffuse map for anything if there is an optimization. We don't want to have to sample lots and lots and lots of points on the specular map to produce our lighting. We want to just do one, right? And so what we want to do here is say, look, the diffuse map needs to produce what you would get if you actually summed the specular answers, right? And the problem that we have here is we didn't normalize our blend. I think that's really all it is. So we're taking these and we're adding them together and we're just multiplying by some stupid coefficient. I don't know why we did this. It doesn't make any sense. It's not energy preserving. If you want to know how much light you would get during the diffuse sample, well, each of those samples that you would have taken weighted by the cosine of them, you can't just add them together because you're trying to produce a sampling of all the different light rays you could have cast. And so they're not necessarily going to sum together, right? That's not realistic of how a surface works. A surface, when light bounces off it, if it's going to bounce light in many directions, it has to be able to bounce that light in the many directions. I'm not trying to say this. So suppose we have 10 photons hitting our surface, right? So we know that incoming there are 10 photons. If we want to say that this surface is diffuse, then fundamentally what we are saying is that it radiates light out in all directions when a light hits it from any direction. So there are cosine weightings there that have to do with how the surface incidence affects how much flow there can be, but fundamentally that's what we're saying. And so if you look at the problem that you have here, if 10 photons hit this surface and you scatter 10 photons in each of these directions, well then what you've done is you've multiplied the total number of photons hitting, in this case by 4x, right? So when we're doing that diffuse blend, what we're effectively doing is taking an accurate representation of how many photons we're hitting our probe, or we're passing through our probe in that case, and we're multiplying them because the diffuse blur is effectively summing them without any weighting. So what we actually need to do is say something closer to this. If 10 photons hit our surface and we want to scatter those photons in 5 directions, we need to send 2 photons out of each of those directions. Now probably the way we need to do this is actually do the scattering weighted by the cosine, like I said. So you probably want to do something more like this, where 1 photon scatters out on either side, and those 2 photons get added here. So it's more like a 4-to-1 kind of a weighting, right? So we probably do want to weight by the incidence to capture that cosine curve, which happens when incident light hits a surface. So we may want to do something like that to try and get a cosine term in there in one way or the other. But what we definitely don't want to do is take a certain amount of power of light coming in and scatter it out in a way that multiplies its intensity. So I'm pretty sure, although I don't know, I'm pretty sure that that's actually the source of our problems. So what I'd like to do is take a look at this routine and figure out where we went wrong, because we know how we went wrong. How we went wrong is we didn't even discuss this, talk about it, or even think about it when we wrote this routine. We literally just smeared the map, right? That's all we did. So we weren't even trying to do a good job here. And so really all we need to do, I think, now is actually try. So when you take a look at what's going on, you can see that there are 2 texels that are in play at any given time. And what we're doing here is we're stepping through the destination. So this is the diffuse. This is where we're producing that blur. And what we're doing is we're taking the specular map and we're smearing that specular map out into the diffuse map. So here's where we here's what we're gonna write to, the txty location of the diffuse map. And then the inner loop is just summing over all of the specular texels, right? So it's basically just picking specular texels, writing them to diffuse. And we did throw in a weight here, and you can see we have a to-do. So it's not like we didn't know we were doing a bad job. We did. It's just knowing you did a bad job is the same as doing a bad job, so now we need to fix it. When we look at how our weighting is distributed, you can see that we're using a cosine fall-off to weight the difference between the incoming and outgoing directions. Whether that's the best way to represent the physical behavior of light in this particular scenario for the performance constraints we have, I'm not sure. So we may want to eventually take a look at how to change how that weighting is working. But what I will say is, let's just leave that for now and say, suppose that is the weighting we need, because we know we will have some weighting that we want there. Suppose that is the weighting we want. How would we then go about and ensure that the power that we then distribute doesn't produce some kind of, doesn't multiply the total power that we would have, right? And so the typical way we would do this is we would say, well, what if we just produce all of the weights that we're going to have, and we then just normalize, do a 1 normalization to say, well, now we want to make sure that this sums to the same amount of power that we had beforehand, so we just take all the weights and we normalize them. The problem that we're going to have here is we never really produce all of the weights, so it's not as simple as just summing them up because we don't actually know what they even are, right? But we do know for any given txty, we do know the opposite thing, right? We have produced all the weights that would sum into it. Right? We just don't know what would sum out of it. But if we looked at the same slot, right? So if we looked at the same slot each time and summed up all of those weights, so if we looked at, here's the diffuse weight map, right? You can see it writing into the diffuse weight map here. If we looked at the same slot in the diffuse weight map and just looked across all txty when we built it, if we summed up those same slots, that would give us the total amount of weight being pulled from that particular spec texel. And if we normalized that, that should give us the correct energy distribution, right? Because that would mean that we were spreading that particular energy source in such a way that it never summed to more than it was originally worth, right? So I think what that means is that, in theory anyway, I think, because I can't think of any reason why it wouldn't work. Let's suppose that we moved this outgoing into here. I think if we just reorganize our loop, because who cares? It doesn't matter which order we do the loops in. If the loop was in this order, it should in theory mean that we can do the entire set of weights for one SY-SX pair, remember them, and then normalize after the fact, I think, right? So in theory, what we should be able to do here is just sum the weights like so, and do one more loop after we're through to just renormalize. So we first loop over all of the destination texels affected by this source texel. We fill in what the weight there should be, and off we go. Now, we don't need to write the weight in this particular case. We just need to sum, right? And we could even sort of pre-compute this value, because one of the things you can see is that well, it doesn't matter. We're pre-computing the whole thing, so I don't even know why I would go down that road. Right? So again, pretty straightforward how this would work. We would then just say, all right, we go through here and we do the same loop twice. First time we just sum how much total weight we're going to have. And I want to say this value should probably, it might vary, but it almost seems like this would be the same for everybody, right? Because it's sort of the same weight octahedral map each way. I might put a thing in here that just says But since I don't really know if the octahedral map actually has that property, I'm just not going to do it because I don't want to introduce that in here, and we don't care because this only runs at startup anyway. So when we go and now produce the actual final values, all we would do is say, well, we'll just divide by the W total now. So instead of writing out the weight by itself, we write out the weight divided by the total weight for that particular texel. And now, in theory, we should have, oops, I didn't realize that was still running. We should have a table that preserves the power of the original light that it sampled rather than having a feedback loop, right? So now when we move around, what we should see is like a lot less light than we were seeing, which is totally fine because we don't have any idea of what these light powers actually are. So the fact that they would be less is totally fine with us. And we don't really know like what these light powers should really even represent. So let's start adding some more light to the world at this point, and we may, like I said, have to kind of think about how much light, what the actual total amount of light would want to be. So I'm going to go in here and put back in some of these lamps, which are like so. Okay. And now what we need to do is, wow, they don't even really bounce hardly any light, which I guess is kind of good. All right, so now what we have to do is start to work on our scale and see, I mean, unless I introduce some kind of a really bad bug, which I may have, right? But it doesn't look like it because you can see that this looks like a sanely behaved lighting source at that point. So what I'd like to do now is just crank up the intensity of these lights to see what happens if we map them in a slightly different way. And we have to start thinking about what we want our power curve to look like for lights anyway. All right, so now we've got, again, our light sources here, and I don't know if that's a sane amount of light or an insane amount of light looking at them, and I'm just going to keep cranking up the power to see what happens, because like I said, we have no idea where on this curve we even are. So for all we know, this is like exactly correct lighting all of a sudden or something like this. Who knows? So you can see at that point we kind of have a weird, I'm not sure what happens when we crank it up to that level of light. And I'm not sure why exactly we would be getting that. So it looks like we still have a bug because in theory it should still stay stable no matter what we crank the light up to, I would think. I could be wrong about that though. Right? So no matter what I crank the light levels up to, we should have been seeing fairly stable light, and we're totally not, right? So I'm guessing that I still kind of have, there's bugs in the propagation here that are making it do kind of weird things, right? And it looks like, I mean, there's a couple things that you have to remember. First of all, there's no ceilings, which creates an incorrect light propagation. So we should probably add those in as well before we start looking at light quality. But on the whole, I want to try and hop down here to the underground as well, because there are ceilings here now, right? So if we take a look at just how the light propagation is working, that just looks like it's not really propagating properly. You know what I mean? So I feel like we've got some bugs in there that we're going to have to look at. And it's not always obvious, though, why. Like, because if you take a look at how how some of the lighting probes look, they look fairly reasonable, though. So it is at least kind of confusing. Right? I kind of want to look at the spec map. First, let me take a look at this routine I wrote and make sure that it's not stupid. I mean, I think it's fairly straightforward, right? You're just saying, I want to produce a blurred version of this map that doesn't introduce any additional power. And so, you know, I've put that in here. I guess I don't know if we really want the outgoing incoming part of this. that part's a little bit harder to determine, because it may actually be that this doesn't make a whole lot of sense. Because if you think about it, when you're sampling the light, I'm not sure. Yeah, I'm not sure how much that cosine fall-off makes sense. But if you assume that it does make sense, then one other thing that we probably also have to consider is that when we do like the raycast and we compute the outgoing values, one of the weird things about it is that I feel like this probably doesn't make a whole lot of sense, because you're kind of double counting it. So I kind of feel like this maybe is not a good thing, right? If we do leave it in there. Now, again, I don't really know to what extent that has any effect. I don't expect it would account for much, right? Yeah, it kind of still looks roughly the same. But I do think that like if we're going to have our probe itself include that, then it seems like you wouldn't want to include it twice, because if you're already doing cosine fall-off of the transmission in the diffuse map, then you wouldn't do that when you sample the map again, right? I mean, that doesn't make a whole lot of sense to me. Yeah. So as to why we're just not getting very good transmission there, I really don't know. And the no ceiling part of it here seems like it makes sense, obviously. But when we go down, I should probably just stick a roof on the orphanage so that we can have a ceiling. But oh crap, I know why. I mean, I don't know why, but I did forget one very important thing. The grid raycaster we have not quite fully enabled yet. So one thing I forgot is that we don't do termination sampling anymore, and we're probably going to have to. So what we want to do here is probably turn termination sampling back on and debug that first. So that was all without termination sampling, and we need termination sampling, so we probably need to do that, right? Okay, so let's take a look at this and restart the debugging process with the grid raycaster actually. Yeah, yep. So that was the problem, right? So now let's take a look and see, because I don't know what the total lighting values would have to be here in order to make this work, but they shouldn't have to be particularly high once you actually have transmission going there, right? So okay, now the cube raycaster will propagate the light, and in terms of how bright you need the lights to be, we can't necessarily determine that there's a feedback loop without doing a power visualization. So there may or may not be feedback loops in it currently, and we kind of have to find out. So if you take a look at how this lighting is looking, it's actually looking freaking great. I'm really liking this. So what we now need to do is write some kind of visualization for the power. Because for example, when it overbrighted there, because we had a 50 times powerful overcolor light, it could have just been the correct lighting, right? It would look ultimately bright, right? So I'm very curious to know essentially like what the total level of light ends up being in terms of situations where you sample. Now, one thing that I'm noticing is that when we use that termination-based sampling, though, it does look like we're getting light leaking again, right? You can see light leaking out here, and I don't care for that. So we'll have to take a look at why we're getting that. It could be that our termination sampling is just a problem, right? But at least unless I'm misunderstanding, when I was looking in here, right, it was able to get outside pretty easily. Like, see that? So we have some issues in terms of how the light leaking is working, and we're going to have to study why that's occurring. But anyway, you can see that the feedback loops are not nearly as... it's not obvious that we even have them, right? So that's also kind of a good thing. All right, so let's make the debug light very powerful and remove these lights and start to work on specific cases now so that we can take a look. So if I go into the world mode and I look at the push light call, what I'm going to do is just increase the power of this debug light, which I believe just requires me doing something like this, right? Like I can, oops, that's not good. Like I can just jack up the power of this light here, and I can, in theory, just have my light be a super bright light, right? And so now when I move around, I will have a light that's powerful enough to do bounces, and you can kind of see that happening here, right? Now the light, again, we're artificially constraining bounce light to be red light and non-bounce light to be white light. So here's with a light that's fairly powerful. You can kind of see it being powerful. And let's see what happens. So you can see this is an example of the light leaking, right? And you can see that these are getting light now, whereas they weren't getting light before. And so I think what we need to do is take a look at how we're doing our termination. When we do a T-terminate, I think the problem that we're having is we're sampling probably the incorrect direction. That's my guess. Or the point is not quite at the right place. Because if you remember, when we call compute voxel irradiance, what we're doing is we're saying, hey, don't allow sampling from any probes that are on the wrong side of whatever it is that we quote-unquote hit, right? And I'm assuming that the problem that we're going to have now is that when you early terminate a grid raycast, it's probably not correctly ignoring some of the light probes, right? So I'm guessing that's what it is because that's the only thing we changed, right? If you take a look at what's going on here, you can see that there's really only two cases where we error out. One is we error out on the apron, and the other is that early out, is we stop on the apron because we didn't hit anything. And the other is that we did an early terminate due to the cost metric. Now, one thing I might do here is actually put this path back in real quick with a sort of a fake thing. In fact, I guess I don't really need to put the path back in per se. What I can do is just make a special if here. And what I want to do is make sure that we're looking at only one case. So inside here, where we look at the node.startIndex spatial grid node terminator, that bit here, what I want to do is put in a like debug do not sum or something, right? Or debug 0, and we'll make that be false. And what I want to do is I want to take this and just say debug 0 equals that. So if we happen to hit the terminator, and I don't mean Arnold Schwarzenegger, if we happen to hit the terminator, I don't want to use the result of that in the light spreading. So when I run this now, what I want to see is it the apron or is it the terminator that produces this problem? And it seems like I can demonstrate pretty clearly here that it doesn't require the terminator, right? Because I think I turned that off and you can still see lighting coming from here. So let's try the other way around. So in here, I'm going to set it to do when we hit the cost metric. So now what we're going to do is we will allow the apron to transmit the light, but we won't allow early outs to transmit the light. And now again, I just want to see if I can spread light outside the boundary in that case, right? And so before it seemed like I was able to do it here, and I'm not. Right? So that seems to me that our early termination code is not producing satisfactory results. And so we need to figure out what we're passing incorrectly there, right? Because something's busted. And we need to figure out what that something is so that we can fix it, right? So let's go ahead and take a look. We now know what the specific case is that we're looking at. And that specific case right here is, you can see how we're generating this. You can see that we're taking the T-terminate and the ray direction, and that's how we're producing what we're going to sample. So you can see that we're sampling, the emission direction and the radii single, all that stuff. I don't believe emission direction is actually getting used. I could be wrong about that. Yeah. So even though in the future we may want to start using that, we're not using it now. So we're really just talking about these two things. And you can see how they're used in here. We use the sample P and the sample N to produce this table that prevents us from sampling from anything that's on the other side of the sample head. Now the probe N single, it's a little hard to know exactly what that should be. Pointing back in the direction of the ray does seem totally fine, but we have to be careful about what location we pick here. So my assumption is that our T-terminate value is not good. If you look at how it works, when we take a step, we also accept the new T-terminate value. So if you look at computing the walk table, the T-terminate value that we write in has already taken its step forward. And I would suspect that's probably the problem. We're probably marching into the next grid square and then taking the sample. But what we want to do is stay in the previous grid square, because if we're not going to process the grid square ahead of us, we don't want to use that T-terminate. So I think we want this, right? We want something that only writes the T-terminate for the previous step so that we'll never sample ahead of where we actually collision detected. Now, I don't know that that was the problem, but I would suspect it would be a problem. It doesn't look like it really helped, because, look at that, right? We're still obviously wrong here. You know what I'm saying? And there's ways we could be creating this problem pretty easily. The fact that this isn't sealed, it could be bouncing up here and then bouncing down. So I don't necessarily know that we have a bug there. In fact, I suppose that's something that we probably need to figure out how to. We probably want the light occluders to be much higher than the walls, right? So let's just try that just to see. So when we do a push occluder in the entity code, this particular part of of the code here, I feel like we need to have two pieces of information when we push the cubes there. So if we look at entity pieces, so I feel like this code needs to have like an occluder size as well, So, we've got bitmap pieces and we've got various things. I feel like we need like an occluder size, right? And I guess that's a little bit easier said than done, because at the moment, it might just be that we should just add occluders as pieces. I think that might just be a better idea. So it might be a better idea to just say, look, there's occluders. Oops, that's the flag. Why are those flags? I guess we just roll the flag. Yeah, all right. Who knows? These don't need to be flags, but our entity system is not really something yet, right? It's kind of just a zygote of something. And so maybe we just have occluders in there. So we would do something like this. And then what we can do is say, yeah, that stuff just doesn't, it's not how that works, right? We're going to push occluders on here as a separate pass. And so, if we actually ran the code now, we would literally have nothing to affect the lighting. The lighting would be completely random because there'd be no walls whatsoever. And then what we'll do is we'll actually, when we create these, whoa. Oops. Sorry about that typo. So now we won't have anything, right? So the light can just spread wherever it wants to spread, right? And it won't be affected by walls whatsoever. And so now what I want to do is actually put occluders in there. And I'm going to draw the occluders for now. So you can see I've pushed a volume outline in there. And what I'm going to do is I'm going to go into the room gen code, and I'm just going to look at how this is working. So you can see where, like, for example, this adds a light to something. So I don't really know how we want this code to work overall, but like, for example, whenever we place walls in here, you can kind of see we've added a thing. We add tags to this. Where do we actually create that entity? It's right here. So we've added an entity, and at some point, I guess we must add pieces to the entity, right? Yeah. So you can see us adding pieces here, and what we want to do now is we'd just add, in addition to that piece, we'd want to also add like the occluder. So we'd say, whatever this thing is, we'd add we'd want one that didn't use the asset category stuff so much. So much like the add piece light call, we'd want like an add piece occluder, and this would just be like, wouldn't have emission. This would just be like it would have a dimension here, probably something like this, offset dimension color, and it would just say, here's the dimension, here's the offset, here's the color, and it's an occluder. So that would allow me to do like add piece occluder anywhere I wanted to, and you don't really need the return value because you wouldn't really modify it. And all you'd be doing is saying, here's the radius in the center, and there's the color, right? Sorry, it's just v3. And so at that point, I think we then would be able to, we would be able to make it a taller, larger bounds, right? And so is it v3 from, how do you create a v3 from, oh, duh, you don't even need to. It's just that. I don't know why I was thinking. Oh, just out to lunch. So at that point, we should be able to now see like occluders around, right? And so there's all of our actual blocks, right? And I kind of forgot that we don't actually put any geometry out here, which is fine. We don't actually need any at the moment. But what I'd like to do now is start to add occluders to that go up to the actual total height, right? So I want these things to be taller. So in order to do that, what I would need in this case is I'd need some way of knowing the top bound of the area in question. And you can see here getting a volume, we have this sort of tile concept, and it can tell me that. So what I'd like to do is look at those calls, because I think we already sort of had an understanding of how these things worked. And we have like a bunch of functions we can actually use. So if you look at like, these get room volumes, get grid, all this stuff, get volume from minimum z is basically saying like, look, if you passed a height in here, what would you, and you looked at the min or max z or whatever, right? If we said get total volume of the tile, that might be more what we want for cases where we're actually adding a wall, right? So I don't really know when we choose to add walls, but it looks like we just have an on wall, right? So what we could do is say, well, there's an occluder and that's just going to be the total volume of this tile, right? So whatever the tile is, it's that. And then if we want to, we can say if we're not on a wall, then we can just say, well, we could even do this. Right? So this just allows us to produce, different occlusion geometry from what we draw, because we want to draw walls at like half height so the player can see. But we want the occluders to be larger, which it looks like we sort of did, but the problem is it looks like it's not quite aligned properly. So when we get the total volume here, we're like producing a fairly odd version of what's going on. So let's take a look at why. Oh, right. We would have to do a make relative. Okay. Because, right, we need it to be relative to whatever the position we're saying the entity is. Okay, so there we go. And now we've got actual blockers in place. And it does look to me like now we've correctly cracked down on that light leakage problem, right? And we'll see, but yeah, it does look like that's significantly less. Now we're still getting a little bit, right? And again, we kind of want to know where that's coming from, so I would like to still kind of hunt that down. It could be coming from stuff that's, even further up, and I suppose we could test that. I don't know to what extent that's likely, but we definitely could test that just by putting a cap on the room as well, right? I really like the idea of having the occluders be totally separate, because that allows me to create real geometry for the lighting, which is what's happening here, while still creating fake geometry for rendering, because you typically don't want to draw a completely sealed room because the player can't see it. And so at the very least, you need to do like wall cutaways or something, which you could do with a render pass, but it's oftentimes just better to let it be an artistic decision. So that has some pretty bad leaking there, right? So I think that would be something we want to take a look at. And you know what? This is a good indication that we have a problem, because this is totally sealed, right? And we're still getting samples. So something's up, and I'm not sure what. Like, how is that getting samples? So let's take a look. Does that happen right out of the gate? It does, right? So now let's go in and see what happens if we turn off the various parts of the grid raycaster. So again, I'm just going to go down and do the same thing I did before. So I guess I'm not sure exactly where I want to do this, but I think I just want to do it right here is probably the easiest place, right? So that would zero it out. And then I can look at what happens in the various cases. So this is apron. Still flickery. Let's try non-apron. And then I'll just try both. Okay. So that's proof positive that I'm still screwing something up with the termination, right? And, that's just a really weird, I don't really even know how that's possible. Something's really busted there. And the reason that I say that is just because those cells that are getting light are not even casting, like where they would terminate would be casts going downward. So how the heck, right? So something's really busted, for example, with how we're doing the probe sample piece single. Something's just messed up, right? And so when we fall out of this and we're going to hit this case, you can see us doing the sample here. I guess the reflect color foo. So the hit ref color in this case is what exactly? Because we haven't hit anything. So the hit ref color is just Fulbright. It's just transmission. The emission level would be based on hit emission, which is nothing, and that's good. So it's really strange. So it seems like this probe sample piece single must be wrong, maybe? That one's really interesting. But you can see that, you know, something's up here. So T-terminate starts at 0. So in theory, it just should not. It should not ever move you forward in that way. I think we're going to have to draw this because I'm not thinking of how that's wrong. Yeah, that's a tricky one. I just can't figure out how you're getting samples when you should never be hitting that case unless you're casting away from where the light is. So how are you picking up any light? You know? Like you can see that it's not picking up any light without the you know, when it's doing bucket brigade carrying, and then if you take that out, it's definitely getting light, you know. And what's more is it's getting light from like below, like it's getting light from like down here, right? How? There's nothing down there to hit, and none of these things. Well, I suppose it could be a feedback where someone down here casts upwards. Yeah, so that's what could be happening. Someone down here casts upwards. The termination sampling is broken. It samples something from up here. And it picks up some of that light. So it could still be that this is just incorrect. So another thing I suppose we could do is, I guess when you're looking in this direction, so you would start at the center of a cell and you take one step forward And if you didn't early terminate, you take another step and you would move from where you were to the edge of the other cell. And no matter what your angle is, I don't see how that would ever possibly leak light at that point. I mean, maybe it could, but it would seem pretty tough, right? I mean, it just doesn't seem likely. I guess one thing we could do is let's try to look at one of those. That's the only thing I can think to do at this point. I'm sorry, I don't have any other ideas at the moment. Using the debug zeroing, we know that something's wrong, and so the question is just, what is it? Okay. So what I want to try and do here is look for that particular, look for something that's down there. So if I that's going to be a much lower value, I assume. Should probably just cold set this thing. It's gonna take me forever to like. We don't have debug value inputs here. So I'm gonna cold set that value quite a bit lower. So I'm gonna set this down to like, I don't know, some much lower number. I don't actually know where we want to be for that lower grid tier. All right, so that's not horrible. But it looks like we're sort of a little too low at that point. So I think that's still one too low for looking at those. Oops. All right, so hopefully this will give us something where we can kind of take a look. I don't actually know. Should probably make a better tester for this. It's been enough times of having to go through stuff that it would be nice to be able to just like click on it and have it like compute which voxel we're talking about. So that looks good. We're basically right in there now. So this is an example of someone who's getting that light. And you can kind of see, I mean, it looks about right in terms of debug output, right? It's stopping on this, and it's doing the point back there. So if I just scan through the rays here, you can see like how they're doing. I suppose what we kind of need to do is say what it actually retrieved, you know? Or why that would be a thing. I want to probably, I'll lock these in so it's 13,586. and 335 as an example. I'd also probably like to draw a little bit lower. So I'm gonna have like the debug dim min z. I'm just gonna drop that. Oops, sorry. I'm gonna take the debug dim z and just add 2 to it, so I get a taller stack. I might actually say let's add quite a bit more to it, just so we get like a nice stack to look at there. Yeah, I don't care about that. All right. Now, how is this thing working? I don't know what this is supposed. Who wrote this code? This is terrible. Like what? That's not what you want. So none of this is right. So you have the total dimension, right? And you subtract away the amount that you were going to show, right? And this leaves how much was left. What you want to do is go up by half of that, right? That's how you'd actually center what you were doing. I don't know what the heck we were writing there. That was some nonsense code. If ever I did see some. All right, so if now we run it, what we should get is a taller stack, right? So at least we can kind of see like what's going on, and you can kind of see like all of these are pointing down. Let's just get the complete stack. So this will just give us like the whole thing. That is, we don't run out of debug lines first. Yeah. We need better support for our debug lines. Fine. For sake of argument, we'll start the voxel at 0 for now. Okay, so here's what we're looking at. And really, it just doesn't make any sense. I don't understand, right? I'm also not sure how the heck, if that's the minimum. I see. It's because that's the minimum that we would sample from, but we can still cast outside of it, right? To pick up light sources, I guess. What was the idea behind that? You know, I don't think that makes any sense. To be completely honest with you, if we think that through, why would we cast out? Why did the voxel being wider, why would that ever help us? Because we can't actually pick up anything other than like pure light sources. I guess we just wanted to be able to transmit light sources. If we're going to do that, though, we don't need very much larger, because since we can't convect any light around, who the heck cares? Like, it would only work if there was an actual physical light source there. It's not going to actually give you any bounce lighting, because we don't actually store any bounce lighting outside of it. So why the voxel itself is larger, I don't know. It doesn't really make any sense. Anyway, fortunately though, this does tell me what I needed to know, which is you can see who's getting lighting. Like And it does look like what's happening is sort of what I feared. Some folks down here who are casting back up at the surface are casting up and able to pick up a lighting sample, right? So if we take a look at, say, this person, we should be able to see where they're getting their light sample from. So let's take a look at that. That's literally on the ground floor, so it should be pretty easy to isolate. And in the meantime, I should just shrink that grid. What's the point? I have no idea why I did that. I think I didn't think that through, because like this just doesn't, it just doesn't make a lot of sense. I mean, a very tiny apron is probably fine, but I don't know. I don't really think that makes a difference. I'm gonna get rid of that because I think that's just a fool's errand. You pretty much have to have your atlas, or it won't work. So, all right. So what I'd like to do is start to take a look at that specifically. And so I'm going to go ahead and grab the debug slider here and just try to pick that one out, which somehow I'm not seeing, which doesn't really make any sense because I should be, right? Oh, wait, I'm still on the apron, right? So I got to get off the apron and then we should get right on there. There we go. Okay. So this is someone who is getting light from above somehow, right? And we don't really know exactly what direction we're getting light from, but we are getting some. And so I'm going to just take a look at some ray indexes here to see if I can, aha. Well, that's an actual hit, though. So that should pretty solidly eliminate any sampling that comes from above it. I'm trying to figure out which direction this is actually coming from, right? It looks like it's kind of coming from that direction, right? Somehow. And so I guess, yeah, something like that. So it looks like it's coming from over there, and I don't actually know how that's happening. Like maybe it's coming from there. Is that roughly the center area or not? No, it's probably a little bit more. So that's probably pretty close, right? I mean, it may not be the exact one, but that looks, you know, at least roughly like I think that's pretty sane, right? So we're somehow getting light transmitted from up here. And I mean, there's a couple of different ways that could be happening. One is we could actually be getting secondary bounce from this. So it could be that something up here actually is creating light that's flowing through. So I guess we should probably look at that. This is what 717531. And so what I assume I want to do is just take a look and see, well, okay, so if that's the actual cast back to here, like where is it, what is it actually picking up over there? So what I might do is lock the Vox start X and Y to also be in the corner, right? And just see what happens there, because I can't tell what lighting is in that area, right? So if I move this stack, I guess I just want to move it over in X a little bit. So maybe I'll do something more like this. And probably want just a little more than that. Oops, that was the wrong way. And so now I should be able to look to see what are the lighting values over there that it's sampling from. Like, is somebody in that region creating light? And is that who we need to debug? Or is somehow this bug? Yeah, I mean, you can sort of see that. It is actually, these folks are getting light from above them, right? Right, you can see like that, but I have no idea how, right? Because how the heck are they getting through here, right? Again, it's kind of a mystery. Now, it's true that there's no floor here, so they are free to cast straight up through here, and that's totally fine, right? But again, I want to know why, right? How are all of these folks getting light when I just don't see where that would really be coming from, right? Are they I'm also very curious what the heck is happening there. So we're gonna have to see what's up with that. There's also sort of a separate issue here that I'm not sure I'm internalizing correctly. I'm not sure I always have these directions proper. Like, I think part of the problem is when you're sampling in a direction like that, it's almost like I feel like we have the normal backwards in a way. When you're sampling a surface that you hit, you sample in a different direction, right? Like, than if you're sampling for transmission. And so I think, I also think I need this. Like, I think we need two separate things. And when you're bouncing off a surface, they're the same. But when you're terminating, they're different. I don't know if that makes sense, right? So basically, like, probably should have used search and replace there, but it's fine. I hate caps lock with a passion. I want my editor to just ignore it. Anyway, I think what we want here is we want to say, when we do a compute voxel radians at, in all of these circumstances, you know, we're going to do probe sample end signal N single, and we're going to pass the emission direction here, and those need to be different. So they'll be the same in some cases, and they'll be different in others. So I think in this case, where you're bouncing off, its emission direction is not what it is, it's the occlusion direction, right? So in some cases, they're the same. So instead of emission direction, we're going to call this occlusion. And what we're going to do here is say that when we do a sample, we will sample in the direction we're heading, but we'll occlude in the reverse direction, right? And then when we actually hit something, that one will be slightly different. So when we actually hit something, we will say that the occlusion direction is the same, right? We want them both to be the same. And then in AABB raycast, it won't really matter which one we do, because we're probably going to get rid of this path eventually anyway. But that's the deal. And so here we pass the occlusion D, and I think that's important because before we were sampling, we were transmitting in a bounce, which is bad. And I could see that creating a lot of issues for us, right? So let's take a quick look now at what's happening down here. Yeah. So do you see how much quieter that is now? There's still probably some bugs in it, but like it's not irradiating between terminators. And I think that's really important because that was basically creating fake reflection that didn't really exist. And now we're not. We're just using transmission. Yeah, look at how much better that is, right? That was crucial. So okay, yeah, that was clearly a problem. So that seems quite good by comparison to what it was, right? Much better. So yeah, so I think we've got a couple things. We're going to need an exposure curve in here pretty soon, because we're, in terms of actually bouncing light around, you can't really use linear 0 to 1 lighting and expect anything to happen. I'm going to try doing some light overflooding stuff, and then we'll save the power curve stuff for next time around. All right, so if I go ahead and do, let's go ahead and jump to where we're pushing that debug light on. I think then we're just about done for today anyway. And I'm going to massively overbright that light. And I just want to see what happens. So we still get a little light leaking there, right? You can see some light leaking happening. It's actually fairly stable, but it's not great. Let's see if I push it up to 30. I just want to see where our breaking point is now. And this is just a good way of testing. Like you can see, like we're getting some weird results. So I think we can probably, I think we still got some bugs in there. Like possibly that may not be algorithm artifacts. That may just be bugs, right? So we should probably do some testing for just like to see if we can use like light over flooding to find any more artifacts there, right? And we'll see. At the moment, however, not bad. So I'm gonna really quickly just restore this to normal, and just see what's up. If I put things back the way they were sort of working before, just curious where we're at, because we're getting there, but we got to put in a curve now. We got to put in a power curve, and then we got to kind of find some debugs there. All right. So looking at the lighting from a high level now, I think the biggest problem we have is just the actual power conserving transmission doesn't spread the light as far as I would like. Again, I think power curve may solve that problem. So we'll have to take a look at that. But starting to get some promising results, right? It's getting much closer. But yeah, again, we have to start looking very carefully at power and trying to figure out exactly how that should go, right? Because we're not getting enough. Oh, you know what else we should do while we're at it? Since we can now, let's add occluders to trees when we place a tree. Because like there was an outside sort of thing we were doing that wasn't very good. And if we go over to don't actually know how we were even doing this. I don't know where we were putting these in. This code is always so kind of weird. Like we haven't really ever made this code good. So I don't know where we're putting tree here. So place tree, I guess. So I think all I really want is to just take that occluder code. So this thing here, if we're going to place a tree, I guess I just make a larger occluder there, right? So maybe it's just this. I'm not sure if that's all I need to do, but it might be. And so if I head over here now to a tree area, I don't actually know, but yeah, so like you can see the occluders are now actually occluding, like the light doesn't spread outside there, right? So we probably don't want as much occlusion from trees. So we probably don't want to do, you know, this, what I literally did. So I'm probably not going to quite do that. But what I might want to do is something more like this. So if we are going to place a tree here, then what I would do is maybe make a little tree vol thing. And just say, well, all right, so the tree vol is going to be I don't know, like the original volume, maybe with an add radius too. I guess I don't really want to start with the original volume, so I probably want to do this. And then I probably want to do an add radius too, I think. I probably actually also want to do a min z here to not have it overflow, but I want to shrink this in, right? So I kind of want to say, well, the tree volume is going to be, you know, less by something, right? So, you know, like we're just going to shrink it down. And I don't know. We actually need to go make our generator code generate worlds that we actually care about. You know, that's a gameplay thing, but I should probably still be drawing those occluders too, because I have no idea what I've just created. But we want something that allows light to kind of flow through those a little bit more. So let me just go ahead and put in the volume outlining, so that way we can at least just see. All right, so that didn't work at all. That's because I didn't actually use the results. All right. So there we go. That thins out the trees a little, but they're still way too tall and also probably still too fat. So we probably want to do this. We probably want a tree vol max z equals, I don't even know. So in terms of like how we can ask about these, when we do the from min z thing, like what is... So it looks like get volume from min z is like produces something from the bottom of the tile up to a particular place, which doesn't really help us in this case. And like looking here, like how do we know where this thing actually starts? Is it at P00 is like where it actually is? I have no idea, right? This code sort of sucks, and it just makes it hard to create things. So let's do this maybe for now. And we'll like worry about creating actual tree occluders that aren't terrible when we actually do the room code. And that could probably stand to be a little smaller yet. Okay. So I'll probably just call that a day, and we can go to Q&A. Is there a reason why that doesn't seem to be shrinking much in Z? Because that should be a quite large Z contraction, but I'm not seeing that. Right? Is it just that Z is much larger, and so it doesn't look like as much of a contraction by comparison, or what's going on there? Yeah, I guess that was. So there's some trees, maybe. All right. So if we take a look now, we should be able to also get some bounce lighting from trees. I mean, in theory, right? So, which now we do, right? And you can kind of see that. Before we were getting complete occlusion there and no bounce, but now we're actually getting some bounce lighting. So we're getting there, slowly but surely. And so now I think our biggest problem is just like we're not getting as much light convection as we would hope. And so I kind of want to know what's up with that, right? And we got to start to analyze that. It's especially kind of strange because I think, again, power curve is really the issue here. Because you can kind of see, like, in fact, if I just go into the shader and turn off the way that we were doing the light flooring, just for interpolation purposes, you can kind of see in here. Where is that? So you can see here where we do our light floor value, right? So the light floor value here, if I just turn off that, which I don't actually know if anyone's properly using it in lighting. Yeah, so we're not even using the light floor pack at the moment like we're supposed to be, but we don't. So if we just went to the light floor value and we just set the light floor value at the moment to be 0, we would see a lot more light in there as well, right? Because right now we're using the light floor in the shader, but not in the actual lighting code, right? So here's the lighting when you don't floor, and you can see there's a lot more light, right? So, you know, it's just better, right? And again, that's just when I say we have power curve issues we have to work out. That's what I mean. So we're really pretty close. I think we're getting pretty darn close here, because we're also quite speedy at this point. We have a lot of debug drawing happening in here, but the actual amount of light computation work is pretty manageable at this point. So I think if we went ahead and stopped doing all of our debug drawing and went from there, I think we're in pretty good shape here. It's looking really nice. And if I go ahead and turn off those occluders again, so let me just turn off the volume outlines, and maybe we'll turn off the debug draw octahedral values as well. So we can just kind of look at the lighting as a sort of a rough state. Should probably get rid of the drawing of the light bounds as well. It's really pretty darn close. So I don't think we've got far to go before we're basically like. And I mean, it's really kind of cool too, because you can see as I hop in front of the doorway, so I move this light there, you can actually see the light starts to go out into the outer area. And when I'm behind it, it doesn't, right? So you get really pretty cool lighting effects happening now. And so as we sort of dial in on the final version, we're really getting some pretty good results. I don't know, these guys don't have their lights still attached. We should probably centralize some of this debug code into like a lighting panel so we can turn on various debug things without me having to go through the code and constantly do all this crap. But you know. So I thought there should be lights on those guys, and there are. They were just really dark. So, you know, let's add actual lights on those guys just for fun. And I think now we can get sort of a sense of, after we do the final set of finishing work. This is also without any ambient at the moment. Yeah, so I think we're gonna be really pretty darn good lighting. I mean, we're only a few sessions away from smoothing out some of these other rough edges here, adapting the power curve, getting the spreading a little better, and reducing the noise, and then this is going to be some really pretty frickin' baller lighting. I mean, zero pre-computation. I think it'll run at 60 FPS. Certainly on newer machines than this one, it definitely will. Doesn't even use a GPU. And we could move it to the GPU at some point too. I just don't know how sensible that is, because in terms of which platforms we can run on and which ones we can't, I'm not sure we want to stress the GPU even more, because, you know, we already want that for drawing, you know, high res and such. So I'm not sure that it makes sense to do that, but yeah. All right, any questions? In the diffuse map weighting divide, could you get a divide by 0? No, you can't, because there is no Because you're always summing over all the possible light directions for the input and the output, we know that the weights will always be at least somewhere non-zero. So there's no way you can have all of the transmission. So between every texel, every spec texel, and every diffuse texel, for a particular spec texel, we know that there cannot be literally zero transfer from that spec texel to all the diffuse texels. A spec texel will, always do a spec texel will always have to affect some diffuse texels, right? With this system, how could we do more physically based rendering looking to the light? So I'm not sure exactly what you mean by that. As far as physically based rendering is concerned, there really isn't a plausible way to do something like that with what we're doing, because we don't even have 3D geometry for most of our stuff, right? And we certainly don't have any material parameters for it because it's just a bitmap that an artist painted. So there isn't really a path towards physically based rendering from here. There just isn't, right? We just don't we fundamentally don't have the source data to explore anything like that. So we can only really look at artistically based lighting. Things like conserving the power, like I did in that diffuse map spread, that's an example of using a PBR style of coding. And I do think you want that. So you want to do some, sort of physical things like conservation of energy. And that's simply for making the system well behaved. But beyond that, I don't really think there's very much we can do. I just don't think there's much you can do when you're just talking about flat sprites, that really have had no, they're just not constructed for this. Does the diffuse bounce use the albedo of the materials? Yeah, it already does. We don't actually look up into the materials because that would be very expensive. So what we do is you just state what you want the occluders bounce to be. So on things that are made of, a reddish material, you can set them red, or if so it's artistically controllable, but we don't actually sample the texture. But yeah, so to give an example of that, if you wanted to, right, when we add those occluders, let me just go ahead and do it. So in the code where we are, is it add piece occluder actually? I guess I don't really remember. Add piece occluder. So what we can do is in these sort of different places here, like let's suppose you wanted, and this is not correct, but let's suppose you wanted for some reason trees to bounce green light, right? And everything else to bounce blue light. And like, I don't know why you would want this, but let's suppose that's what you were doing. What we can do is just change which occluders we're adding there, and then what you can see, hopefully, is that all of the secondary bounce lighting now has a blue tinge to it, and you can kind of see it, pretty clearly, like in here and in here, right? And then all of the trees would not, like they'll have an extra green bounce to them, right? So, I mean, because our bounce lighting is really muted right now, it's harder to see, but that's, that's what that is. Maybe I should make it red since everything is green out there. I'm not sure you could really see the fact that it was green, but you get the idea. I'll make it yellow. So we do use it, but because the diffuse bounces are a lot more muted than we would like, you just don't see it as much, right? And that's why we need to start getting the light power curve under control, so you'd actually get some of those effects. And I still can't really see much bounce lighting, which is sort of a problem out here, which is a bit of an issue. But obviously these will all still be blue, and you can see that they are. But the bounce lighting for these guys, I just don't see, right? I like just don't see it at all. So I'm not sure what's up with that. We may just have to look at it a little more carefully. Let me try it with red. One of the problems is everything in that area is green, so it's kind of hard. It's like already kind of not something that bounces. Yeah, so you can sort of see it now, right? You can see the red tinge. So we are using it. It's just that because direct lighting is so much brighter than our indirect lighting right now, which is, again, I think because we need to start working on like the transmission exposure levels. I think that one of the problems we're going to have is just that until we do that, you don't see, you really just don't see the bounce lighting as much as you should. Can you compare with the older raycast? I suppose we might be able to. Obviously, there's some issues with the older raycast in terms of how it convects light, but we certainly can. Let me try. The older raycast has ambient lighting, and we haven't put that into the new raycast yet, so it would have a slightly different effect. Although, you know what? No, it doesn't, because we turned it off, so I guess that's fine. So no, it doesn't. So yeah, so in terms of actual light cost, we also can't really, we haven't pulled the debug code out of our grid raycaster, so we actually can't tell how fast the grid raycaster is at the moment either, which is another thing. So it's hard to necessarily compare these two, and we also haven't tuned the grid raycaster, so it's a little premature to do the comparison, but there's certainly nothing wrong with this raycaster. Like, it's fine. I just don't think at the end of the day we'll be able to quite get it up as fast as I need it to be. Whereas I think the other one I will be able to. After the shader modification, it appears the light is still leaking. Why is that? So actually, even before we were messing with the shader at all, we still have some light leakage that I demonstrated early in the stream. I don't know if you remember. So we know it's there, and we have to look and see whether it's a natural artifact of what's going on or not. Some light leakage. Well, I guess this has a ton of light leakage. This is the wrong caster. Hold on a second. I'm not sure why there was that much in there, but yeah, I'm not sure what was going on there. But if you take a look at what's happening here, there's actually, or at least there was, and I'm pretty sure still is. Let me just try and make it happen again. Some more obvious light leakage. So I can't make it happen just at the immediate moment. There was some obvious light leakage happening earlier that I wanted to take a closer look at. It's not happening now. Like that is quite solid actually. So I'm not totally sure. I think there's some still light leakage thing we want to look at. For whatever reason, I'm not able to actually make it happen again. So I don't know, maybe we accidentally fixed it completely, but I don't think we did. So I was going to look at some more light leakage issues later. At the moment, I can't seem to get it to do any light leakage at all, which is great. I mean, hey, it's nice that I can't make it do that, but I'm not sure why. So yeah, you know, there's that. Yeah, and I don't know why I'm not seeing the light leakage anymore. I guess we fixed it more than I thought we did. Because I thought there were still some flickery problems with certain folks out kind of in the distance there. So I don't know. At the very least, when we did light flooding, so, I mean, at the very least, when we do light flooding, we can see that it eventually does bounce around, I thought, unless I'm just misremembering. So if I go in and do a push light here, and I just, like, really over flood the lighting, I think this leaks out, right? And that was fairly conclusive. See? So eventually it does get outside, right? If you push enough power through it. So it's not perfectly sealed, which, again, there is no ceiling on this thing, so technically that could actually be correct. It could be that a light that strong in our system should propagate outside because there is no sealed ceiling. If we actually put a sealed ceiling on, then obviously that shouldn't happen. So I don't really know. And you know, maybe one thing that we should do is actually create that thing that, although our room gen needs to be like actually written hardcore so we can make things easily with it, and we're pretty freaking far from that right now. It probably isn't the worst idea for me to try and put occluders in on non-wall sections that are just the ceiling. I probably should do that. So if we were going to do that, I guess what I would need to do is say, if there wasn't a room, I don't know exactly how we would do this, but it's probably something like taking the max Z of the wall. So like, if we're not on a wall, but we are inside, I don't know what that means. Like, how do we know if we're inside or not? So it's spec outdoors. So I guess we would say, like, if we're not on a wall and we're not outdoors, then we need to add a ceiling tile, right? So we would say, like, okay, like, give me a ceiling, and we just need to know how do we create that ceiling. And so to do this, we would need to presumably just take the whole tile, and then I guess we'd just say, like, look, the min Z equals the max Z, and then we just create a thickness, you know, so minus some very thin thing. So in terms of, like, trying to seal, right? Do you see what I did there? So there's like this, you know, set of ceiling tiles now, so that the light is inside only, and you know, at that point, I should be able to over dial that light, and it shouldn't be able to get outside. Now, I don't know if that will actually happen, because I think we do have some light leaking bugs still, but that's, now at least we know that it's sealed inside there, right? So now when you really like push that light level, you can see what ends up happening. And you can see that it still does get out, right? So there is some way that light eventually can get out. And again, with an inexact algorithm like this, where we're trying to save a lot of computation time by not doing a whole slew of things, that may be unavoidable. So I'm not really concerned about that, but I do want to do it as testing, if that makes sense, so that in the future we know definitively whether there's additional bugs causing light leaking or whether it's just an artifact of the approximations of the algorithm that makes the light leak. Either way, I'm happy that now we really don't have much light leaking in the game proper, right? Like if you just look at the normal way this would be played, there's no light leaking. So it's mostly just quality concerns that I want to increase the, just want to denoise and blur is basically all we really need to do at this point, I think. Right? But it's looking really nice. So let me see what are those other questions. Is it possible to smooth out the lighting? Oh yeah, I mean, I will smooth it out. I probably will be able to get it till where it's perfectly smooth. Would be my guess. I kind of have some ideas on how I want to do that, but I'm just not interested in that right now because we still have like accuracy issues. I can look at a noisy solution and go, is that actually producing the correct solution? I can already sort of tell that we need a power curve in there, and we need to like work on that transmissive stuff a little bit better. So we've got things we need to do first before we work on denoise. From what I've perceived watching Handmade Heroes, lighting has taken up a pretty sizable chunk of the episodes. Is lighting inherently complex? Yes. Lighting is by far the most difficult thing you can do in graphics, period. There's nothing even close to as hard as lighting that I know of. Literally anything you want to do in graphics is easier than lighting. Photons are the fastest moving things in the known universe, and they are the most plentiful things in the known universe. So you are inherently simulating the very hardest thing you possibly can. There's nothing as bad as lighting. For fixing the square interpolation, that's just because our samples are on a grid. So what we want to do there is just in the shader where we sample it, we just want to blur those out, right? So really it's just a sampling issue. So it's the question of what's the fastest that we can do, right? Will there be topics which we spend as much time as light? No, there's nothing as hard as lighting. I don't think there's anything you can pick that would take as much time as lighting. Even fluid simulation such as plasma? Yeah, so fluid simulation is significantly easier than lighting. Much, much easier than lighting. And the reason for that is fluid simulation has... so inherently all physical phenomena have a propagation rate, is the way to think about it. So all physical phenomena that we simulate in games are inherently three-dimensional, or you could think of them as four-dimensional, depending on how you want to look at it, right? But everything we simulate in games is three-dimensional. We sometimes make two-dimensional versions of things or whatever, right? But inherently, everything is a three-dimensional phenomenon from the real world that we're trying to do inside a game, right? And each one of those physical phenomena have propagation rates, which determine how much of the system they can affect and how quickly. Lighting has the fastest propagation rate. It propagates by photons, which are the fastest moving things in the known universe. There is no phenomenon harder than that. Fluid simulation usually can only propagate at the speed of sound or worse. So sound is much slower than light. And because all physical phenomenon tend to happen at the speed of sound, not the speed of light, it's always easier. The region you're trying to affect on every frame of update is inherently contracted dramatically. Whereas lighting could literally affect the entire world pretty much in one frame. So like game worlds are basically the size that a photon could span in like one frame, right? So yeah, fluid dynamics much easier than lighting. Now neither are easy, and the reason for that is that it has the same sorts of problems, meaning that we can't possibly hope to simulate the behavior of all of these molecules. So, you know. Networking is trivial compared to lighting. I wouldn't consider networking even remotely in the same class of problem difficulty as lighting to me. I mean, they're not even they're not even a little bit scary to me, right? So it seems like when you walk, you drag the light behind you with inertia, more like a liquid. Is that on purpose or an effective computation program? No, that's specifically because there's no way for us to do it fast enough, right? If we move to a GPU, if we were saying this is an RTX 2080 game always or something, we could have it be instant. And that's because our geometry is very simple. A AAA 3D game has just dramatically more geometric complexity than we do. So they always still have to have a few frames of latency with their indirect lighting. There's nothing they can really do about that. But because we have such a simplistic set of geometry, if we wanted to require very high-end 3D hardware for this game, we could make the lighting instant probably. So you wouldn't see that lag. But it is 100% an artifact of what I just said, which is that lighting is like the hardest thing, and you can't really do it right. It's not possible. So. So yeah, I don't really want to argue with people on the chat. You're welcome to think whatever you want is complex. I've been a programmer for almost 35 years. I know what is complex and what is not, and what is difficult and what is not. Networking it's not trivial, but compared to lighting, it's cakewalk. Period. I mean, and you're welcome to disagree with me, but I don't really care, because what you think is hard, you may think lots of things are hard that I don't find hard, right? So, not really super relevant to me. If you have a hard time programming game networking, then, fine, but I don't. So it's not something that scares me. right? Lighting scares me a lot. And the reason for that is because it's so complex and so difficult to approximate well, and no one's ever done it. Tons of people have network games that work well. Tons of people have network games that work poorly, but tons of people have things that work poorly all the time. So, lighting is a problem that literally no one's ever shipped a good solution for in history in real time, whereas tons of games have good networking, right? Just because some games have really terrible networking doesn't mean anything, right? People write crappy stuff all the time. But literally no one's ever shipped real-time indirect lighting ever in anything that actually worked, right? Doesn't happen. So we're always a few frames behind, right? We're always doing weird approximations, and it's always kind of wrong. So, and that's just the way it is, right? What is so special in RTX? Well, there's nothing special in RTX. It's just that when you have hardware that can do dramatically more raycasts per second, then it becomes much easier to do fast lighting updates, right? Because all of our slowness that we don't really know how to work around. The diffuse blur we can work around and make much faster probably than we have at the moment. But the other half of things is the raycasting, and we really just don't have ways of making that dramatically faster than what we're currently doing, at least not that I know of. And so we're kind of always gated on that. Whereas if you have special purpose hardware that can do it way, way more raycasts, way, way faster, which an RTX would do, that's just a really big deal, right? Is the difficulty of global illumination part of the reason why you're doing it? Sure. I mean, it's mostly just because, it's something that if you want to do a professional quality engine, you need to reckon with at some point, right? So I feel like it's something we should at least cover and do a reasonable job of, because it gives you some perspective in just how hard this problem is, right? So, and maybe someday NVIDIA will save us, right? Once you throw enough simulation hardware at the problem, maybe it can just go away, but at the moment we're just kind of screwed, right? Yeah, the RTX version of Minecraft might have noticeable light lag in it, but remember, again, they've probably got way more geometry to worry about than we do. Because even though we sort of look a little Minecrafty because we've got like blocky things, we're only looking top down at like a room. Minecraft, you're like looking out, at the world, and there's just so much more geometry there that, it's the raycasting cost is proportional to the geometric density of the scene, right? And we have the ability to limit that geometric density a lot more than a game like Minecraft has a first-person perspective. So I guess that's what I would say. If someone were making a different game with much sparser scenes containing more complex geometry, well, wait, which are they? Are they sparser or more complex? I guess they're sparse but complex. Would you have an alternative prescription? Could the probes be arranged in a sparse grid or in camera frustum space rather than world space? So a sparse arrangement of probes would be difficult. And the reason it's difficult, not because computation on it would be much more difficult, but because the shader in the GPU used to look up the lighting samples would be more expensive, and I'm not sure how far you want to go down that route before it becomes prohibitively expensive, right? Arranging them in a grid that isn't world space, so like you said, camera frustum space, that seems more doable, because as long as you have some affine mapping from pixels to whatever this space is, I think that would, that would certainly be feasible. I don't know to what extent people have tried that. One of the problems that you're going to often have is that there's two things you're trying to do here. One is like you correctly identified, you're trying to make sure that you spend the most amount of time computing lighting on things that you can see on the screen. So you want things that are close to the camera to have more time spent on them, certainly, than things far away. The problem is that light needs to be simulated, and it may be that a lot of simulation time may be necessary to move the light from something distant into a way that just makes something distant look brighter than it, so that you can see it. So even though that's a very small thing on the screen, figuring out that it should be lit might cost a lot, because you needed to do a bunch of crazy bounce lighting out there. That's why lighting is so hard. It doesn't really yield to those kind of approximations as well as you would hope, which is why we introduce all these other artistic approximations, because at the end of the day, accurate lighting is just sort of impossible, and probably always will be. So what we're going for is never accurate lighting. It's just approximate lighting. And when I say maybe NVIDIA will save us, it's approximate lighting that they'll be giving us, but fast approximate lighting. Accurate lighting, forget it. It's not possible. When you tested secondary bounces with red light, it seemed like it only worked in the left and down directions. So if it could be the case that we have a bug there, and I'm not really sure if we do or don't. Like I said, we're still in the process of trying to kind of like fix everything in the lighting system and make sure it all works well. But I don't actually know whether we've gotten to that point yet. Because we're doing a lot of crazy stuff like sampling the voxels using occlusion, it's entirely possible that a bug in that inclusion code. So for example, this code here, if this code here were broken, that would be a pretty easy way to get directional bias in how light was spreading, right? Because when you go to sample a voxel, it would be sampling the voxel only in like it would be knocking out people who shouldn't have been knocked out based on the occlusion normal or something, based on like an error in this code, right? I don't know. One question I do have here is, did we ever stop to look to see whether this is correct? So this is saying, like, isn't this the wrong way around? Kind of. Like, did we actually look at this? So that's the point that we're sampling from. So we're basically saying from the corner to the point we're sampling from. And then we're looking at the normal. So this is like what direction we want it to be able to go. We're basically trying to say that those need to be same-sided. We should just really quickly make sure that's true. I suspect it probably would have shown up as a very obvious error, especially with the light leaking, but I don't know. Let's just check. So if you imagine we have this, and we're talking about a particular UVW point here. So if we want to sample a particular direction, so let's say the particular direction we're sampling in this case is this way, then what we want to do is we want to imagine that there is a plane passing through here, and these will then be disqualified from sampling because they can't possibly have hit this and then gone in that direction, right? So what we would like to do is say, is the direction the same? And it looks like it is. Looks like we did do it correctly, right? So we're subtracting UVW. We're doing UVW minus the corner, and that is what we want. So again, just wanted to reassure myself that that wasn't obviously busted. Again, I think it would have shown up, but I just want to make sure. How does an RTX card actually perform ray tracing? Is it similar to what the PS5 can provide, which is hardware to work on a BVH structure to perform ray tracing, or is that different? So I guess what I would say is I don't actually know much about what's on an RTX card because I don't know that they've ever told anyone. I mean, maybe they have, but I haven't followed it very closely. In general, I can tell you more the reason why these hardware solutions can get you better results than a CPU. The reason is because the primary work involved in tracing array is actually very simple. There's not a lot to it, as you know. Testing whether an array hits a triangle doesn't really require a lot of work. The problem is that you're trying to do lots of these tests and, usually you, like you said, use a bounding volume hierarchy. And what happens is as you traverse through that bounding volume hierarchy, you're typically basically creating completely unpredictable code. So every step, the better your bounding volume hierarchy is, the more random the walks through it will be. Because each ray will be classified very cleanly into the stuff it can and can't hit. And that just creates an incredibly unpredictable path with unpredictable cache usage through this memory that you then have to op on. And modern CPUs are low core count, generally speaking, high predictability optimizing machines. They really like doing highly predictable things in a small number of cores. That's what they tend to do. And that's the exact opposite of what a bounding volume hierarchy traversal is. So what custom hardware does for graphics processing is they typically kind of take an opposite approach. They will basically crank the number of I guess we call them hyperthreads on the CPU side. But basically what they'll do is they'll say, look, let's just accept the fact that we have no freaking clue how this thing is going to want to walk through this memory. And what we'll do instead is we'll just launch like a tremendous number of rays at a time through the system. So while one ray is unpredictably trying to fetch the stuff in the bounding volume hierarchy that it's going to need next, we always have more rays in the pipeline who can have computations done on them. So typically what happens on a GPU that's very different from a CPU is whereas a CPU maybe has 2 hyperthreads per core at maximum, a GPU might have dozens, right? It might just have tons and tons and tons and tons of ray bundles stacked up waiting to flow through this pipeline. So even though you have no idea what memory you're going to use next, and it might take you a while to go and fetch it, there's always somebody else ready to use the hardware. And so what ends up happening is they can just stamp down lots of units that have lots of hyperthreads and then just worry about feeding those with a tremendous amount of memory bandwidth. And even though they are doing computations, any individual floating point operation on, say, an NVIDIA GPU is probably much slower than a CPU. It doesn't matter because the actual total throughput is much, much higher, right? So they have more units running more hyperthreads. And so even though they are clocked lower typically, they can just get way, way more throughput for something like ray tracing. I don't know much about the PS5, so I can't tell you if there's anything special going on there. But generally speaking, I would suspect that RTX or PS5 or anything else, I don't think there's any particularly secret sauce to it. I think it's mostly just, look, tons and tons of hyperthreads on lots and lots of little microcores is how you get good ray tracing performance, and CPUs aren't that, right? Are the probes in the wall still getting cleared to 0? Yes. No. I don't know that they get cleared to 0. They just aren't allowed to cast. Yeah, and just to be clear, so what I was talking about was not ray incoherence, actually. So ray incoherence is a different phenomenon. Ray incoherence is when you're trying to trace a bundle of, say, 16 rays at a time because you're using a wide vector unit to do the computations. What the problem you have there is that if one ray hits very early, but another ray takes quite a bit more computation to generate the hit that it will produce, you end up spending as much time on all the rays as the most expensive ray in that bundle. And that's just an artifact of any SIMD computation. So obviously there's a whole separate set of work that goes into trying to limit that extra cost. But that's not the same as the unpredictable walk problem, which even if you're only doing one ray still occurs, right? The fact that you don't know what part of the bounding volume hierarchy you will need to load until after you've already done your computation makes cache streaming suck, right? Makes the memory streaming suck. And so you can't walk through that bounding volume hierarchy at anything close to the same speed as you can actually compute what to do. So maybe it takes you only a few cycles to determine which side of the bounding volume hierarchy to traverse. It doesn't matter because you can't possibly load it fast enough, right? Modern CPUs rely on... So in order for a modern CPU to get good performance, it has to be able to predict what memory you will use before you use it. If it can't, then your performance will be horrible, period. That's just the end of the story. And the problem with a thing like a bounding volume hierarchy is the whole point of the bounding volume hierarchy is you don't know what part of it you're going to end up in. If you did, you wouldn't need the bounding volume hierarchy. So fundamentally speaking, when you're talking about something like ray tracing very geometrically dense scenes, the problem that you have and have to surmount is that you need a completely unpredictable traversal through a bounding volume hierarchy, but you know that that is very slow. So typically what they will do, like I said, to solve this problem, is accept that that will be slow and just do a ton of them together. So as one piece of memory comes into the system, we do the ops for it, we issue the fetch to get the next part of the bounding volume hierarchy, and then we immediately switch to a new set of rays. You know what I'm saying? So basically we just make that pipeline deep enough that the memory that's coming in, even though it takes a tremendous amount of latency to get that memory, it doesn't matter because we're issuing so many different memory fetches that one of them is always coming back as we finish the computation for another one, right? So we always keep it fed. And that's what I was talking about when I was saying the unpredictability. Ray incoherence is not that. Ray incoherence is different. And it has to do with packing. They're called warps in GPU parlance, but they're just SIMD lanes. It's when you pack multiple rays because you need to be able to do them together. And like I said, there's other ways to do that. In our system, we actually don't do that. Right now, what we do is multiple volumes against one ray, and you can pick which one you're doing, right? All right. I think we're at the end of the questions. Sounds like. All right. Thank you everyone for joining me for the episode of Handmade here. It's been a pleasure coding with you as always. If you would like to follow along the stories at home, you can always head over to handmadehero.org and pre-order the game. It comes with a source code so you can follow along with it at home. I will be back here next week, I believe. Is that true? Yes. I will be back here next weekend to take a look at improving the lighting quality. I think we've done some pretty good work here, but we now have to kind of smooth out those rough edges. We have to look at the power curve of the lighting, and we have to look at the that interpolation smoothing. So there's a couple different things we want to do that can really, dramatically improve how good the lighting appears to be without really even improving any of the underlying like ray casting or sampling. So that's what we're going to start moving into over the next few weeks as we go. So hope to see you back here for that. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.